One of the most important tools that a physicist can have is the ability to manipulate and use vectors. Are among the most important tools that a physicist has when trying to solve problems, particularly problems that involve forces, it really does. They just touch on so many things. So what is a vector? Today we're going to talk about vectors and scalars. A vector is a quantity that has both a magnitude and a direction. That means that, an example of a vector might be a velocity, where I'm moving at 5 meters per second north, as opposed to a scalar, which is a quantity with a magnitude but no direction. A scalar would be I'm moving at 5 meters per second, where I have 2 markers, something like that has no direction attached to it. Some of the most common vectors are listed here that we're going to see: displacement, velocity, acceleration, force, momentum, the electric and magnetic fields, scalars, distance, speed, mass, time, temperature, and charge. You can think about this because velocity, it makes sense to be moving in a certain direction. But mass is just a mass. It doesn't have a direction component to it. So that's one way to try to remember the vectors and scalars. What I did here, too, is displacement, the magnitude of displacement. When I say magnitude, I mean the magnitude here. I'm talking about the length of the vector, the number that goes with it. So if I push this table with 5 newtons, then my magnitude is 5 newtons. And it turns out that there are scalars which are the magnitude of certain vectors. The magnitude of displacement is called distance, and is a scalar. The magnitude of velocity is called speed, which is a scalar. The rest of these don't have corresponding scalars. Magnitude of acceleration is just called magnitude of acceleration. So, an interesting, why do we use this? They have interesting results. They're not always the same thing. For example, if I start here, and I walk to the other side of the board, and I stop, and I turn around, and then I walk back, and if I end where I started, my displacement is 0, even though my distance is certainly not 0. The reason for that is because my displacement, if I started here, my displacement was I moved here, and then I moved back, which means I started and ended at the same spot, which means if I take into account the direction, I didn't move at all. My displacement is 0. However, the distance I covered, this is the amount that I actually walked. I walked over here and I walked back. I definitely burned some calories, not many, but I moved and I walked, and that's my distance. So distance is path dependent, and displacement is path independent. So let's say I walk a really crazy path. Let's say I start here and I walk all around the place. Maybe I can cross over a few times, and then I end right here. My distance is substantial. This entire path, I have to add up all the parts of this path, and that'll give me my distance. To find displacement, you just draw a straight line between the 2 points. And that's my displacement. So displacement, which we write as d with a vector sign over it, this little half arrow hat, shows that it's a vector. This is always going to be, the magnitude of that is going to always be less than or equal to the distance traveled, so just normal d. Kind of a confusing notation. But all you really need to know is that's how you figure out the displacement and the distance, and how you get those 2 values. So let's look at an example other than this one. So vectors are drawn as arrows. So let's say I start here, and I take a path that looks like this. Let's say this is 2 meters, 4 meters, 2 meters, 4 meters. So we need to ask ourselves, I want to know what is the displacement and what is the distance that is covered by this person walking around. So take a moment and think about that. Turns out that my ending position is the same as my starting position. So because of that, my displacement is yet again 0. The distance I travel, however, I walk around this whole path here, So the distance I travel is 2 plus 4 plus 2 plus 4 is equal to 12. So I traveled 12 meters, but my displacement was 0. So when you draw vectors, as you can kind of see here, you're always going to, I'm going to erase this. When you draw vectors, you always draw them head to tail. So what I mean by that is if you want to draw this vector and plus this vector, you're going to do it, you can pick either one to do first, you'll get the same answer. So let's start with the one on the left. So I'm going to go here, then I'm going to take this vector's tail and put it at the head of this vector. And I've added those two vectors together. But what's my answer? 3 plus 3 isn't just 3 plus 3, you get a number. So the answer here is another vector, and it's going to start where you start, and it's going to end where you end. So we're just going to draw an arrow like that, and that's called my resultant vector. And you get the same thing if you started with this one. So we can go up, and then we can go right, and you can see that once again, we started here, ended here, and they don't look exactly the same. They are. These, I just didn't draw it very accurately, but these two vectors are the same vector. So just like in algebra, A plus B equals B plus A. So those are the same. Subtraction is a little bit different, but still relatively straightforward. So subtraction, if I want to do this vector minus this vector, all you're going to do is flip the direction of the second vector, the vector being subtracted. So I start with here, and instead of going up, I'm still going to put tail to head, but this time I'm flipping it 180 degrees. So it goes down. And then I draw my resultant vector, and I get this. So that's how you add and subtract vectors. Vectors cannot quite be multiplied by another vector or divided by another vector. There are two operations called the cross product and the dot product, which we might get to later on, that you can use, but not straightforward multiplication. However, you can multiply it by a scalar. If I say,
Are you kidding?
hey guys.
Nikki's waiting here and she's like, can we go? You came here.